Hello all, I welcome you to this series of lectures on speaker verification. I am Matilda Sagai Mary NJ. I am a PhD student under Professor Umesh. I majorly work on speaker verification. So what is verification? Verification is something we do very often, right? Like checking the photo in the ID card a person carries and seeing if it matches the face of the person. And for the purpose of verification, not just ID cards, people even use fingerprints, retinal scans. Okay, so to perform verification, we need something unique that is the characteristic of a particular speaker. So a retina, it's unique to a speaker. Face, yeah, it is unique to a speaker, but then in the case of twins, it will fail. So similarly, speech is also unique. Okay, a person's speech. The manner in which he or she speaks, okay, it's different and it's unique. So speech can also be used to perform verification. So that's what speaker verification is all about. So in the lectures we'll try to cover, first we'll give you an introduction on speaker verification, and then we'll talk about two conventional techniques to perform speaker verification. UBM-GMM, which is Universal Background Model, Gaussian Mixture Model based speaker verification, is one of the earliest speaker verification systems. Then vector based systems came and I-vectors is one such system, and it's also conventional and it's been there for a very long time. After which came the speaker embeddings from neural networks. Okay, so once the neural networks caught attention, people try to get some embeddings from the neural networks and try to perform speaker verification with those embeddings. Okay, X vectors is one of the it's the first work, okay, in the neural network based speaker embeddings. And then came R vectors, and S vectors is by the Speech Lab IIT Madras. It's the in-house neural network based speaker embeddings. Okay, so once we extract the speaker embeddings, we have to perform some scoring to identify whether it is from the same speaker or not. You put a threshold on the scores, and if it is greater than the threshold, you accept that it's from the same speaker, and if it is lesser than the threshold, you say that it's from the different speaker. But to get those scores, we need some techniques. We have the embeddings, okay, but to get the scores, we need some techniques. So we have PLDA, which is probabilistic linear discriminant analysis, and a simple cosine similarity, which is nothing but the cos theta of the theta, where theta is the angle between the two embeddings. Okay, and then Tessa, which is transformer encoder speaker authenticator. This is again an in-house technique. Now let's look into what speaker verification is and how it is done. Let's say I want to build a speaker verification system for Alice and Bob. Okay, I want to build a speaker verification system. For this purpose, because I am going to use speech of the people as the basis for speaker verification, I have to record speech of Alice and speech of Bob and keep a database with me. So what is verification? A person makes a claim that he or she is some person, and then the verification system has to say, okay, it is the same person, or no, it is not the same person. Okay, so there is an unknown person. He comes to the verification system and says, hey, I am Alice, let me in. Okay, because this verification system is going to act like a security that is sitting near a gate. Okay, so this is a gate. I'll say speaker verification system is like a security who can either open the gate or close the gate. Okay, security guard. So this unknown person claims that he or she is Alice. Because it is a speaker verification system, we'll take the speech of this unknown person, and because this person claimed that he or she is Alice, we'll have to take the speech of Alice, okay, and compare and generate some scores, right? And this is like a gate. So this score, if it is greater than some threshold, okay, we'll accept that X is Alice, else reject. So what happens if, so red here, let's say it marks the score is lesser than threshold. So this gate is not opened. Okay. Our security guard, the speaker verification system, is not going to open the gate. If the score is higher, green here marks score is greater than threshold. Okay. What does that mean? Person X is Alice. Okay, this is the decision made by your speaker verification system. And then the gate is opened by our security guard, which is your speaker verification system. Okay. And the person is let inside, right? So this person is let inside. This could actually mean the person is given access. Person is given access to all the information Alice has stored, right? So will the speaker verification system be always correct? No, it is going to make some errors, right? So this person may not be Alice at all, but the speaker verification system can just say that, oh, it seems like Alice voice, I'll let them in, right? Let this person inside. So that's one type of error it can make. Sometimes it can be Alice, but the system might say that, no, this doesn't sound like Alice voice, so I'm not going to let this person in. So this speaker verification system is not going to be 100% correct, okay? So we are still far away from putting it to like use for very sensitive applications, I would say. So one more parallel area which is often confused with speaker verification is identification. Okay, there is a subtle difference between speaker verification and speaker identification. Both are going to use speech only, right? Because it's in the term itself, right? Speaker identification. So you are going to use speech again. So in a speaker verification system, this unknown person always makes a claim about his or her identity. Okay. So as we saw before, this unknown person made a claim, right? He or she made a claim that he or she is Alice, right? So what did the speaker verification system actually do? It just tried to answer this question, is it really Alice? This is the question that speaker verification system answered, right? When it comes to speaker identification, there is no claim at all. There is an unknown person, but no claim. This is the major difference between identification and verification. There is no claim. What is a speaker identification system supposed to do? It is just going to figure out whose voice is this. It goes to see, searches in its database and finds out whose voice is this. Okay, so this can be either Alice's voice or Bob. So the answer will be Alice or Bob, right? What will be the answer here? Yes or no? This is the difference between speaker verification and speaker identification. Now when it comes to speaker verification systems, there are two types. One is text dependent, another one is text independent. As the name suggests, in a text dependent system, along with the speech, you have speech. Along with the speech, you have the knowledge of, okay, this is a plus sign I just wanted to put, okay. You have the knowledge of the text that has been spoken. Let's say Alice comes and says, hi, this is Alice. Or Alice can even say, hello, good morning. Okay. So a text dependent speaker verification system has access to the text that is spoken. In a text independent system, no text, just speech. Just the speech waveform, whatever Alice spoke. Just speech, right? Okay. So, in a text dependent system, the system knows the text that is spoken, and sometimes there are techniques to use the knowledge of the text that has been spoken to improve the system performance also. Some cases that you can think of is a text being displayed and then you ask the person to read it out. You have seen in many websites, right? Like you have to just type in the phrase that is put there, right? Or a captcha image, right? You have to just type in. Similarly, it can be a word and then the person might be asked to just speak it out. So in that case, the system knows, right? The word is already given and the person is just going to read out the same. So the knowledge of the text is present. So those are the examples of text dependent systems. In a text independent system, obviously there is no knowledge of text and it is independent, right? The person is free to speak whatever comes to his or her mind. It's more flexible, but the problem is very difficult. In this set of lectures, we will be focusing only on text independent speaker verification systems. Next, we will move on to the conventional speaker verification systems, where I mentioned UBM-GMM based methods, which is one of the earliest speaker verification technique, and then a vector based technique which has been there for a longer time, which is I-vectors, and then we will slowly move on to the neural network based speaker embeddings, and then finally how to score them. So one of the earliest speaker verification techniques is UBM-GMM based technique. UBM-GMM means universal background model Gaussian mixture model. Okay, so it's UBM Gaussian mixture GMM, okay, model. That's what this is. Okay, so to perform a UBM-GMM based speaker verification, first you need to have features. Okay, you would have recorded speech, correct? And from speech you do feature extraction. So this is mostly MFCCs. This you must have seen in the earliest set of lectures of this course. Okay, how to extract MFCCs. And then you build two models. One is called the target model. Second one is your background model. Okay. Both these models are GMM models. This is also a GMM model, and target model is again a GMM model only. Okay, this is also a GMM model. Again, GMMs have been discussed previously in this course. So what is a GMM? You can represent a data as a mixture of Gaussians. So that's your GMM model, and then you can find the probability for a data point from it, right? It's a generative model. So you have speech features extracted. To build a background model, you use the features from all the utterances of all the speakers. Say you have 10 speakers and each speaker gave you 5 utterances. Okay, then you will have how many? 50 utterances, and for all these 50 utterances you do feature extraction. And with these I'm going to build a GMM. Let's say I am in 2D space and I have a 2 mixture Gaussian. Okay, this is one. I will not draw it like this. Okay, this is x2, x1. Let's say this is the GMM that I built with all the utterances of all the speakers together. So this GMM I will call it as UBM-GMM, universal background, right? Universal, all speakers, right? Okay. Then I have to build a target model. So let's say I want to perform speaker verification for Alice. Let's say the claim is, the unknown person claims his or her identity to be Alice. Then I will use the target model of Alice. If the person claims Bob, then I will use the target model of Bob. Okay. So how many target models I will have? As many speakers as I want to verify. Correct? Okay. To get the target model, what you do? Background model, we used all the utterances of all the speakers. Target model, because it is a target model and it is specific to the speaker, right? I'll use only the that particular speaker's utterances here, not all the utterances. Okay. So if I'm going to build a target model for Alice, then only Alice's speech is going to be used. If it is for Bob, then only Bob's speech is going to be used. So the number of target models will be number of speakers, okay, for which I have to perform speaker verification. So how is this target model obtained? Okay, you are going to take this UBM-GMM as the start point. So you will take UBM-GMM is the starting step, okay, and you will do some adaptation, okay, wherein this clusters, right, this mixture that's there, after adaptation might look something like this, based on the speaker, okay, might look like this. Let's say after adaptation, this is what looks like for Alice. For Bob, it might look something like this. So different speakers will have different target models, okay. And as I mentioned before, from a GMM you can find the probability of getting a data point, right? So once these models are all ready with us, what you will do is, if I am going to perform speaker verification for the claim Alice, I will take the UBM-GMM, correct, this UBM-GMM, and I will take Alice GMM, which is adapted from the UBM-GMM, okay, and I will try to find, so this is already with us, right, and the person would have claimed that his or her identity is Alice. I will take that speech, okay, and get the features. I will find out the probability of getting those features given that it is generated by the target model, and the probability of getting those features given that it is not by the target model, which is actually the UBM-GMM, okay. We are saying that the features have come from UBM-GMM model. Here we say that the features have come from the target model or the Alice model, because the person claims that he or she is Alice. So I have two probabilities with me. I will perform a log likelihood ratio test, which is LLR test. So this is how it is calculated, the log likelihood ratio. Log of the probability that the claimed feature, okay, is from the target model minus log of the probability that the claimed feature is not from the target model. If this value is greater than a threshold, this threshold is to be set by us, okay, we'll adjust it accordingly and see which is acceptable and all. We'll accept that it is from Alice because the person has claimed that he or she is Alice. If it is lesser, we are going to say that, okay, no, this person is not Alice, and we are not going to allow the person to access the data of Alice. So this is UBM-GMM based speaker verification. Next conventional technique that has been there for a longer time is I-vectors. This is one of the first vector based speaker verification that came out, okay. So for I-vectors too, we need the understanding of UBM-GMM and something called super vectors, okay. So in a GMM, I just want to go back to show you. In a GMM, this is a 2D GMM with two mixtures, right? If this is my class center, or not class center, I would rather say the mean of the first mixture, and this is the mean of the second mixture. Okay. Then how do I represent this mean? Let me draw it again for clarity. Let's say this is one mixture and this is another mixture component. Okay. So two mixture, 2D GMM. Okay. So let's say this is some mixture center. How do I represent that? Mixture 1 mean is given by sum x1, x2, x1 m1, x2 m1. What would be mixture 2 mean? That's also like x1 m2, x2 m2. Okay. What I am calling it as x1 m2 is this. This is x1 m2. This is x1 m1. Okay. This is x2 m1, x2 m2. Okay. So when the means of the GMM are stacked, in the sense I'll put them like this. I'm just stacking them. This stacked vector is called a supervector. Okay. This is called a supervector. Now if there are k components, in this example we had two components of j dimensional GMM. This is again a 2-dimensional GMM. What is the resultant supervector's dimension? It is k cross j, 2 cross 2, so 4 cross 1. You will get a 4 cross 1 vector. So that's your supervector. Okay. So what does I-vector say is, again I am not getting into too much details of I-vectors. There is something called a speaker and channel dependent supervector, capital M, and M is speaker independent supervector. Because it is speaker independent, so it has to come from the UBM-GMM. You remember, right? Like when we built the background model, a universal background model, it was from all the utterances. So it is speaker in all the utterances of all the speakers. So it is speaker independent. Okay. Both are related by capital M equal to M plus T into W, where T is called a total variability matrix. And when it is related like this, this W corresponds to the I vector. Okay. So with these vectors, you perform scoring. You get the I vectors and then give it for scoring. And then set some threshold. Set threshold. So I vectors are called as identity vectors, or sometimes called as intermediate vectors. Okay, because they have lower dimension compared to the speaker and channel dependent supervector. Okay, so this completes the conventional techniques in speaker verification. And as the neural networks caught on, the newer techniques came into picture. So with the neural networks, people tried to tap some embeddings, and those embeddings were used for speaker verification. So it is one way advantageous because I'm going to perform verification on the embeddings, not on the speech directly. So I need not store speech. Just embeddings. So I save a lot of space, right? Means I have cut down the cost, right? I have cut down the cost. Okay. So instead of speech database, I have an embedding database. And here too, after the voice is taken, you compute the embedding. So this is like some vector, okay? This is some k cross 1 vector. This is again k cross 1 vector. And they are given to the speaker verification system, and some scoring is done. Based on that, you allow or not allow, that's decided. Now, these embeddings can be obtained from different type of neural networks, and based on the type of neural networks from which the embeddings are obtained, they get different names. So, you have X vectors, R vectors and S vectors. X vectors are from time delayed neural networks. R vectors are from ResNet based networks, and S vectors are from transformer encoder based networks. This is in-house by IITM Speech Lab. So to obtain speaker embeddings, there are different steps to be followed. First, you will train a neural network. For what purpose is something important, and it has to be noted. We train a neural network for speaker classification. Okay, it's not directly trained for speaker verification. Rather, it is trained for speaker classification with a large number of speakers, something like around 7,000. Okay, and mostly the results and the research that happens uses this database called Voxceleb. So you train the model to do speaker classification. So in the output layer of the architecture, how many nodes will be there? Output layer of the architecture. Speaker classification architecture. Will have 7,000 nodes if there are 7,000 speakers in the database. Okay. So once it is trained to classify the speakers, then from the network, okay, you tap at some point. Tap the network. Which network? The speaker classification network. Tap the trained speaker classification network. Okay. And then you get the speaker embeddings, and then give those embeddings for scoring. Now, let's say I want to perform speaker verification for a speaker who is not present in this 7,000. Okay. Let's say Alice's speech is not at all present in this training data of the speaker classification network. The beauty is still I can perform speaker verification for Alice. That's the beauty of this neural network based speaker verification. So as mentioned before, there are 3 speaker classification architectures that we will be discussing in detail: X vectors, R vectors and S vectors. And the speaker classification architectures use a different lots of loss functions, and research is still on. Different loss functions are giving improvements over the existing loss functions. So a plain softmax, L softmax, A softmax, which is like angular margin softmax, AAM is additive angular margin softmax, L is large margin softmax, but will not get into the details of all these loss functions. Just know that different loss functions, there is lots of research going on, and they are giving improvements in the final scoring stage. Okay. And once the embeddings are with us, we can perform scoring, and there are three existing techniques to do scoring. One is PLDA, which is probabilistic linear discriminant analysis, a plain cosine scoring, and an in-house Tessa, transformer encoder speaker authenticator. So first we will see the details of how the speaker classification architectures are built for the three cases.